I made a pass and play version of Pool for the Game Boy Advance. Now I know everyone is familiar with the extremely popular GBA pool games like Hardcore Pool and Killer Pool 3D and Archer McLean's 3D Pool. So you might be asking, Jacob, what makes yours different? And I'll tell you right now, the main difference is that mine is worse. It's just kind of objective. But I made mine by myself in a little over a month. I'm assuming the rest of these were all made by teams of people, at professional studios over months. So relatively, it's pretty cool. I decided to make Pool on the GBA for two reasons. Reason one, I wanted to make a physics, collision detection engine thing. The coding and the math fundamentals can be used in so many types of games and applications, so it just seemed to be valuable. And reason two, I wanted to take a generic C++ tutorial and implement it specifically for the GBA, and then also expand on it. And Pool seemed to hit all of those marks really well, so Pool it was. The tutorial I picked about collision detection and physics was from this YouTube channel, JVidX9, or the One Lone Coder, who has some amazing videos on game development and other C++ concepts, and no videos on GBA programming. My goal was to take this tutorial, code it up, make it work on the GBA, and then make a working pool game and make, whatever optimizations I needed along the way. Okay, I'm here at my desktop in a different shirt with a little demo program to explain the core of the physics engine and also to give a quick computer science lesson. Right now, the code just initializes the screen, prints hello world, and then we'll sit in this loop. I'll go ahead and make the project. And it's done. We'll go ahead and start it, and boom, hello world. Just to prove that this actually is the code that I'm building, we'll go hello YouTube. We'll go ahead and make it one more time. And then we will run it again, and boom, hello YouTube. In Pool, we'll need to update the balls on the table every frame, and we can do that with a simple for loop. I'm just going to print the values of the balls instead of updating them, but the idea is the same. And you might notice in Pool there are 16 balls on the table, including the cue ball. I'm just going to use 15 for the sake of this demo. It'll give us a round number later. So we can go ahead and make this. Oh, forgot to save. Oopsies. Go ahead and make that. And then we'll go ahead and run it again, and boom, just prints through every ball value. For detecting collisions, we'll need to check every ball against every other ball to see if they have collided. And we can do that with a nested for loop like this. So just like before, I'm going to iterate through every ball, and then I'm going to also check the target ball to see if the two have collided. Again, not doing any collision detection, I'm just going to print out the current ball, the target ball, and then the total number of checks. So we can go ahead and make sure that's saved, build it, and then we can run it. And you can see for comparing 15 balls to each other, we need to do 225 calculations. What about if this number needed to be 30? Just double the amount of balls. We can go ahead and make it one more time, and then run it. And this is going to take a second. You can see we doubled the amount of balls, but we actually have to do 4 times the amount of checks. This concept is called time complexity, and the general idea is how much longer will your code take to run as you increase the size of the input. A nested for loop like this has a time complexity of n squared, which is not efficient at all, and generally you want to avoid a complexity of n squared. But for a small input like 16 balls in Pool, it should be fine. What you can do is include optimizations so that most of the time you do not have to do n squared calculations or comparisons. Technically, the time complexity will still be n squared because in the worst case scenario, you will have to do n squared calculations, but it should be able to avoid this most of the time. And there are more complex algorithms that can do this more efficiently, but the tutorial didn't use them, so I'm not going to use them either. Unless the situation calls for it, but I don't think it will. End result of the tutorial, well, 2 tutorials actually, is a physics engine with ball collisions and line detection that utilizes the mouse to drag or move the balls. Let's think through what needs to happen to make it run on the GBA. We can skip on the drawing and moving lines because the pool table will be stationary and I can just hard code those boundaries onto the table. We do need to be able to draw the balls to the screen, and to state the obvious, the GBA does not have a mouse and keyboard, so we need to address that as well. Balls have a pretty obvious solution in sprites. Sprites are individual entities that can be loaded and drawn to the screen. They can be anywhere from 8x8 pixels to 64x64, and they can even be combined with other sprites to make even bigger images. To start out, we can just use 16x16 balls as placeholders, and we will make sure that these are affine sprites, which allows for rotating. An important note about sprites is that their X and Y coordinate is actually in the top left corner of the sprite. Since all balls have this same quirk, we shouldn't need to address it in the code actually. It should just recognize that they're all bumping into each other the same way, and it should work out. Now, handling the mouse features will be a little bit tricky. The tutorial uses a drag and release method to click on a ball, drag in a direction, and then kind of like Angry Birds, send the ball flying in the opposite direction. It does this by setting a velocity equal to the X and Y distance from the mouse release point to the center of the ball. Since we don't have a mouse, I'm going to use trigonometry. I'll add a value to our ball sprites for the angle that the ball will travel, that I can modify with the left and right triggers, and an arrow to the ball just as a visual indicator of what direction it's facing. Then, by using the magical sine and cosine values, I can get the X and Y velocity to send in that direction. Those values will be normalized, meaning they'll only travel 1 unit in whatever direction they're sent. To change the velocity, I'm just going to hold the A button to charge up a power value. And then when I release, I can multiply those X and Y velocities from before by the power value. And now the balls are flying off in a direction. Now, turning this into pools shouldn't be too much of a challenge. My initial mockup looked something like this. No measuring or scaling or plan for the bottom portion at all, but that would reveal itself to me later, once I figured out how much space I would actually have down there. After some brief research, I found the table dimensions of the playable green area are 2:1. With the 1 tile border around the whole table and a screen width of 240, that leaves the playable area as 224 pixels wide. And using the ratio that I just found, that would mean there would be a height of 112 pixels. If we fill out the rest of the dimensions, we see there's 32 pixels of space below that, which would be perfect to show the sunk balls and maybe some text about whose turn it is, and then eventually who wins the game. With these dimensions, there's just no way that we can use 16x16 balls. But I don't really want to use 8x8 texture for them. They just won't have enough detail when they render. And I can do both, but this option does introduce some other considerations. Because the balls are displayed using affine sprites, I can scale them so that they use the 16x16 textures, but they'll only appear as 8x8 sprites. There is some loss of detail when they're scaled, but I think the hardware actually handles it really well. The last parts of the table are the table borders and the pockets. I can add lines from the tutorial between the pockets, and I don't need to worry about rendering them because they'll just be part of the table background. I just hard-coded an array of 6 lines because it honestly doesn't need to be harder than that. The pockets are similar. They'll be drawn as 16x16 black circles onto the background, but will actually be 8x8 balls placed in the center of those black circles that check for collisions with other balls. If any ball collides with the pocket, they'll be considered sunk and then removed from the board. The actual last part is the turn logic. I can use a few Boolean values for who is stripes, whose turn it is, if their shot was taken, and then also how many balls each player has left. I can then use those values to decide if a player gets another turn, if they can go for a ball, if they sank a ball for the other player. There are almost surely rules that I'm going to miss and did miss, but overall it functions pretty similar to actual pool. Okay, so I got the engine working, and I got all the visualizations in place, and I got the turn logic going. Let's go in for a game. Okay, hoping for an amazing break, and oh my goodness, this is slow. Time to crack down on some of those optimizations, the collision detection. Oh my. The first place I'm gonna look for are some of those nested for loops. How can I weed out meaningless calculations as early as possible? The biggest one we can get out of the way is in the first layer of the nested loops. If a ball isn't moving, there's no reason I need to check if it's going to collide with another ball. If it is going to collide with another ball, that's because the other ball is moving. So I can just let that ball handle the collision. I created an FPS counter just to work on improvements for this code. Check out my YouTube short on that. And this optimization alone more than tripled the frame rate. If you want to see more about little tools like the FPS counter that I built, subscribe. Super easy, and it lets me know that this stuff sounds interesting to other people. In a similar vein, I added some checks for the walls, pockets, and ball collisions, where before the collision check even occurs, I do a simple comparison of the positions. And if the two entities that are going to collide are far enough apart, I won't even check for a collision. These values were kind of arbitrary and could be optimized a little bit more, but these optimizations were not nearly as influential as the previous one. Lastly, when checking for collisions, the code handles one collision between two balls twice. Once immediately when the collision is detected, I push each ball away from each other, and then again when the velocities are updated using the physics. There are a few identical values that are being calculated for both situations, and they're not cheap values to calculate. Specifically, there are two division calculations and a square root. If you aren't aware, computers are bad at division, and even worse at square roots, so avoiding redoing these calculations can be really helpful. So I stored these values when the collision was handled immediately, and then reused those values when the collision was handled properly, instead of recalculating them. And again, these were not nearly as influential as the first improvement, but are noticeable, especially on the break when a lot of collisions are happening at the same time. To wrap up this project and finally call it done, I added player displays that show whose turn it is and what balls they sunk, and a happy little crown that bounces up and down when a winner is declared. This was a really fun project, and I'm super happy with the results. I'm very proud to say I feel much more confident coding collision detection and physics engines, and will definitely use these new skills on something in the near future. As always, this project is not perfect, and I probably won't take the time to make it perfect, but that's okay. The important thing to me was to accept that fact early and do it anyway. If you want to look at the code or download the .gba file for yourself, I've included the GBA version of the tutorial and the final version of Pool on my GitHub page, and the .gba files are under the release section on that same page. I've added links to the tutorials I followed and the GitHub page in the description below. Also, did you know that billiards is the umbrella term for all sports that use a cue stick, including pool? The more you know. All right, thanks for watching.